NMR integration and coupling. Have you got it? This short video quiz assesses your understanding of chemical shift, integration, and spin-spin coupling in proton NMR spectroscopy, and your ability to predict the proton NMR spectrum for a given molecular structure. The quiz consists of 3 questions. It's meant to be taken after you have studied the material and you think you understand it. During the presentation, you'll be asked to pause the video to at least try to solve the problem yourself and only then to continue. It won't be hardly as effective if you jump to the solution immediately. Okay, here we go. Number 1, given the compound below and its spectrum, assign the letters A to F to carbons on the structure bearing those hydrogens. Selected regions of the spectrum are magnified so that you can see the splitting better. Explain everything you can about the spectrum. Okay, pause the video. See what you can do. Come up with everything you can that explains the spectrum, and I'll get back to you. Okay, we're back. How did you do? First, I'm going to draw the hydrogens on these various carbons. And I'm going to figure out what the formula is. Okay, and we have some groups of equivalent hydrogens, these 2 methyl groups of the isopropyl, these 2 hydrogens that are flanking the carbonyl group, these 2 hydrogens that are flanking the oxygen of the ether, the CH2 on the oxygen, and the CH3 over here. We expect to see, oh, and one more, the H of the isopropyl. So we have 1, 2, 3, 4, 5, 6 expected signals, and in fact we have 1, 2, 3, 4, 5, 6, A, B, C, D, E, F that we can assign. So that's everything. They're all here. They're all accounted for. Okay, so let's see if we can find these 6 groups and assign them on a spectrum. Well, we do have 2 signals down here in the aromatic region, and those are from our 2 signals coming off the benzene ring. And we've talked about this before. The ones that are downfield, these A ones, are going to be flanking the carbonyl group, and the ones that are upfield are the B, shielded by the oxygen in that ring with its resonance contribution. C on the spectrum is around 4. That would be a group on the oxygen. We see from the integration that it's 2. That's our CH2 then. D is a signal that's split many times, and if you look really carefully up here, you might be able to see that that signal is at least 1, 2, 3, 4, 5, 6 lines. In fact, it's 7 lines. It's hard to see the little wings of those sometimes, but that's because it's this one over here next to the carbonyl group. Remember that anything to the left of 2.0 a little bit is a hydrogen on a carbon next to a carbonyl group. So that's what we have here. And it's 1 hydrogen. And then E, if we look carefully over here, E is a triplet, 3 hydrogens. So that's a methyl group, a CH3, next to a CH2. That would be this guy over here. And finally, we have this tall signal split into 2. That's actually our 6 hydrogens from the 2 methyl groups of the isopropyl being split by the hydrogen of the isopropyl. So that's the basic assignment. Is there anything else we can see here? Well, let's just go through that splitting again, make sure that all looks good. A is being split by B by this coupling that's due to the adjacency on the benzene ring. C and E are being coupled. That's our ethyl group. And D and F are being coupled. That's our isopropyl group. So that all looks really good. All the chemical shifts are what we expect. We have the aromatic region. We have the region where there's some oxygen and the hydrogen is on the carbon next to the oxygen. We have this carbonyl group, hydrogen next to that, and we have a couple of alkyl groups which are not actually attached to any functional group directly. They're attached to other carbons that are attached to the functional groups. Well, how'd you do? Number 2, for each H, work out the expected proton-proton splitting pattern, indicating the splitting designation as singlet, doublet, triplet, quartet, doublet, doublet, double triplets, double quartets, doublet, 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 etc. Take your time. Graph paper works really nicely for this, but if you don't have graph paper, just kind of sketch it out, see how well you can do. Restart the video and we'll talk about it. Okay, here we go. Did you figure it out? Some of these are a little tricky. Let's start with A. We have a coupling constant with B of 2 and a coupling constant with C of 10. Okay, it doesn't really matter which order you do this in. I like to start with the larger one and then work in the smaller one. So our first coupling I'm going to work with is HA to HC. That's 10, 5 each way. And then each one of these signals is split into 2 by a 2 Hertz coupling with B. That's just this little coupling like this. And so what we expect to see is a doublet of doublets. Okay, how about B? Well, B is coupled again by 2 to A, but then it's also coupled to C by 16. And each of those is split by 2 for A. So one to the left, one to the right. And that's another doublet of doublets. Okay, how about C? Well, C's a little tricky because C has coupling to A and to B and to D. And the decoupling is 6. Okay, so this is actually going to be pretty tricky. Actually, you know what I'm going to do? I'm going to come back to this one. I'm going to do D first because I think that's easier. D is only coupled to C, so that coupling is a 6 Hertz coupling. It's 3 this way, and our signal for D is a doublet. All right, now what about this C? Well, all right, this is tricky. 16, 10, and then 6. All right, first the 16. I'm going to do this down here. The 16, that's 8 to the left and 8 to the right, followed by 10. That's 5 to the left and 5 to the right. That looks right. Now, here's the deal. Each one of these is a quartet with a coupling of 6. Now, the quartet itself is actually made this way. You go 3 to the left and 3 to the right. Then from that one, you go 3 to the left and 3 to the right. Takes us right back to the middle. 3 to the left, 3 to the right. Now that middle one is doubled, so I'm going to make it twice as long. Now, we go 3 to the left and 3 to the right. And we go 3 to the left, and now we add a 2 long to a 1 long, and 3 to the right. And that's a 2. But now, this one coming in from the right also adds to this one and goes to the right. So, there is our quartet. But each one of these is going to produce that same pattern, and I'm just going to kind of do a dotted line down to here. and reproduce that pattern again. Let's see what this thing looks like. Okay, it's a pattern that looks like this. Okay, so that's what it is. And this thing is a 1 to 3 to 1 to 3 to 4 to 1 to 6 to 1 to 4 to 3 to 1 to 3 to 1 multiplet. Okay. Officially, this is called a doublet of doublets of quartets. However, we would probably call it a multiplet and just leave it as a whole bunch of lines rather than actually ever work that out. All right, enough of that. Here we go. Number 3. Here's a challenge, as if that wasn't a challenge. Draw this compound's expected proton NMR spectrum based on what you know of chemical shift. Do not use any tables. See how close you can come. Pause the video, see what you can do, and I'll show you the spectrum. Okay, here we go. First of all, I'm going to find the groups again. This time I'm not going to draw the H's. We're going to expect 1, 2, 3, 4, 5, 6 groups again. Okay, starting with A, we have 6H, B is 1H, C is 2H, D is 2H, E is 2H, and F is 3H. Chemical shift-wise, we expect the A to be somewhere around 1, F also to be somewhere around 1, B somewhere between 3 and 4, well, maybe call it 3.5. The shielded oxygen one around 6.8. Protons adjacent to the carbonyl group around 8.1 maybe. And the protons in E adjacent to the carbonyl group at, we'll say 2.2. Okay, couplings. Our 6H are split by one hydrogen, so that's a doublet. The 1H is split by the 6 hydrogens, so that's a septet. Each of the hydrogens in the aromatic ring are adjacent to one hydrogen, so that's a doublet, another doublet. E is the CH2 of an ethyl group. It's next to 3 hydrogens, so that's a quartet. And F is a methyl group next to 2 hydrogens, so it's triplet. There we go. See if we can draw it. Septet. Quartet at 2.2. And I've got a doublet down here at around 1, and a triplet also a 1. I don't know. I guess I see the oxygen over there. Maybe that's going to be electron withdrawing or something. I'm just gonna do it like this. Triplet. Okay. And the integrations of these are 2H, 2H, 1H, 2H, 6H, and 3H. That's what I think. What do you think? Shall we see what it really looks like? This is actually a prediction. This isn't the actual spectrum, so it could be a little bit off. How'd I do? Oh, I was a little off on that isopropyl, wasn't I? Everything else looks pretty good, but I underestimated the chemical shift of the CH on the O. I put it more at a place where it'd be a OCH3, but actually it's way over here at about 4.8. I guess that's because of the benzene ring. The oxygen is actually pulling electrons, especially away. Those electrons are being pulled into the benzene ring, and it's especially sucking electrons away from that CH. All right, well that's it. That's how it goes. Remember, integration of a proton spectrum gives us the relative number of atoms within a set of identical hydrogens. An atom's signal will be split by hydrogens that are within 2 to 3 bonds of that atom. The size of the splitting depends upon the coupling constants between the atoms and can range from 0 to about 15 Hertz. Each coupled atom splits the signal once. Coupling constants for H atoms on benzene rings and within alkyl chains average about 7 Hertz, leading to recognizable patterns such as doublets, triplets, and quartets, the N+1 rule. Other couplings lead to more interesting patterns, such as doublet-doublet, double-triplet, double-quartet, WW, and ultimately we lose track and we just call them multiplets. Finally, analysis of integration and coupling provides essential information for structure determination. All right, I hope that was helpful, and I hope you've got it.